Okay. Now we define energy flux. So idea is this equation I wrote some time back, no. So this is TUK. So I now integrate this over a sphere. So I think I have the example of a sphere. This is sphere. So this is, imagine a 3D sphere, yellow sphere. So I told you that energy is coming via nonlinear term. So we focus on energy via nonlinear term. So this P mode, which is the giver mode, is inside the sphere, P inside the sphere, and K is outside sphere, right. I mean Kx Ky Kc, that is outside. So it turns out energy in 3D typically flows from P to K, small wave number to large wave numbers. So there will be energy going from P to K on average. Okay. So that is in fact is breaking the Riedel balance. Somebody is giving energy to somebody. Okay. K is not giving as much energy back to P. Sometimes it may give, but it is basically taking from P. Okay. So now we want one number. So I would say all the P modes inside the sphere, how much energy it gives to the modes outside the sphere. It is one number. So the energy flux is from all the P modes. So this is we call it energy going from P to K. P is a giver, K is a receiver, and Q is called mediator. Okay. Q is not really giving or taking, but it is like a lawyer. Okay. So P is given to K, but P is inside the sphere. The sphere radius is K naught. The radius of the sphere is K naught. So P is inside the sphere, but K is outside the sphere. K is outside the sphere. K is greater than K naught. So this is the flux. This is the definition of energy flux, which is energy going from modes inside the sphere to modes outside the sphere. Got it? And in 3D, this is greater than 0. Is property of the Navier-Stokes equation. Okay. It has been proven by Kolmogorov. The energy will flow from a large scale to small scale. Large scale means small wave number. Okay. So large scale is here and is going to a small scale here. In fact, we inject energy at close to the origin, small wave number. So okay, I am not proving it. This is not objective of this course. Well, I will show by field theory that this will be indeed positive, but I will not prove by Kolmogorov theory. Okay. Kolmogorov showed this in his 1941 paper. Okay. So that is by nonlinear term, but this equation has other terms, this force injection and the dissipation. So any questions on what I did so far? I am kind of going very fast, I would say. But any questions on what I have done, talked about so far? Everybody is clear? Well, some of these guys know turbulence. Huh? So if you do not know turbulence, you should ask. Any questions? So just to recap, so in hydrodynamics, we are like in this room. So this is the source of, well, fan you should think of, AC is with more. So fan is giving energy in this for the fluid in this room. So, but it is large scale. Fan is not of the size of the room, but of course big fan. And this energy which is injected by the fan is getting dissipated at small scales, but via cascade. Energy injected by the fan scale is going down and finally it dissipates. So that is the picture. Okay. I will show you some more results, but that is the idea you should think of. And this is not a thermodynamic system, right? You can see that it is definitely not like a thermodynamic gas where so thermodynamics is single scale phenomena. So I think let us get it recorded. I think this is a good example. So I will, so let's record this as well. So is that clear? This is, the idea is clear. And non-equilibrium is basically multi-scale. Okay, that is what I would say. Okay, so basically we discussed this nonlinear term, how it's giving energy from large scale to small scale. This is a which one? This is a flux, the blue arrow. But it requires that I have something injected here. So in a room, the example would be a fan, or in a coffee cup I stir by the spoon. So that is large scale. The energy fed at that large scale is getting down and it goes down like that, it goes to small scale and dissipates at small scale. It, in fact, kinetic energy is lost by viscosity. Viscosity basically eats up the kinetic energy. Okay. And so, we are injecting energy, this is the injection by large scale, okay. And this is naturally a multi scale phenomenon, right, is going from the scale of the fan in a room to small scale at mostly like, well, like micron scale, okay, that is what micron scale. So, this is a multi scale transfer, and this is very different thermodynamics, which is a single scale phenomena. In thermodynamics, what do we have? These molecules are hitting each other, and the length scale there is the mean free path length. We do not have phenomena across scales in a thermodynamic gas. Of course, the gas in this room is multi scale, but then we have this big, it turns out there are big vortex where the molecules are of course going locally, but also there is a net velocity. Okay. So, this is a multi scale phenomena we got. Okay. Now, there is one example which I would like to emphasize, and with that I can derive Kolmogorov theory. Okay. So, I can intuitively give a stuff. So, imagine, so there is a white sphere and there is a orange sphere. So, the white sphere, the flux is pi uk, this is a flux coming out. There is a flux coming from the orange sphere, pi k plus dk. Are they equal in general scenario? They will not be equal if there is a energy injection by this green arrow. Of course, normally I said in Kolmogorov theory energy is injected at large scale, small k, but energy can be injected at all scales like in gravity. So, if there is energy injection, then this will be bigger, right, orange sphere will give more energy out under steady state. So, if I inject something, then this is coming in, but I give some more money in the system. So, this will have more money going out. So, that is a positive source of flux, but there is a dissipation in this orange shell, and that will decrease the flux. So, the competition between pi uk and duk, and that is d pi by dk. Okay. So, so this is one more example, the coffee cup. So, this is a multi scale transfer like that. Okay. Now, imagine for Kolmogorov theory, we say energy is injected only here at large scale. So, in between the region, this is 0. Also, in the intermediate range, the duk is small, it is not 0, but small. So, you can ignore it. Then what happens? This pi uk is constant. Okay. So, that is the Kolmogorov theory. Kolmogorov theory assumes that energy is injected at large scale and dissipates at small scale. So, that is where you get pi u to be constant, and this is the non-equilibrium scenario where we are getting cascade of energy. Now, given the constant flux, we can derive what is energy at a different scale. So, this is the called energy spectrum. Okay. Remember, I had said E k dk is total energy. Okay. So, what is the unit of E of k? Is E total energy by k. Total energy is u squared by u squared, not total, and k is 1 by length. So, this. So, the unit of E u k is L cube by T squared. Okay. So, now E u k will, there are some more arguments, but I am going to do it fast. So, E u k is function of pi or the dissipation energy injection rate, which is same as cascade, alpha and k to the power beta. So, we know the units of epsilon, which is energy supply rate is u squared by T, and k is L to the power minus 1. So, you match the units both sides, then we derive this formula, this one. So, kinetic energy spectrum is k minus 5/3, this flux to the power 2/3, and a non-dimensional constant called Kolmogorov constant. Okay. So, this is the Kolmogorov famous spectrum, and this number is approximately 1.6 or 1.7 or 1.8, depends on people. Well, but normally people believe it is between 1.6 and 1.7. Okay. So, this is the derivation. I will leave it for you to complete as homework, and you do that. Okay. Now, given the spectrum, I can derive quite a few interesting things. First of all, this is a verification in simulation. The spectrum we did a DNS, but this is the like done by thousands of people, both experiment and simulation. This is 5/3 line is spectrum, and flux is constant. This is valid only in the inertial range. This range is called dissipation range, and this is the forcing band. Okay. Now, let us derive few interesting observations from Kolmogorov theory. So, I can look at the energy in a band of wave number. So, k to k plus dk. Okay. So, there is a band k to k plus dk. Now, again I am just going to say that this is a power law of physics. So, this k plus dk is going in logarithmic scale. So, my k plus dk is 2k. Okay. Now, you just believe me that this is how we do it for power law of physics. So, when I integrate this, k minus 5/3 will give you my k minus 2/3. Okay. And this is important step, my dk is k. So, my UL squared is epsilon 2/3, k is 1 by length, so L 2/3. So, what is UL? UL is, I take the square root, I will get epsilon u 1/3, L 1/3. This is the cascade rate. Given this, I can look at the diffusion coefficient. What is the unit of diffusion coefficient? It is centimeter square per second, or it is length time velocity scale. So, what is diffusion? So, our molecules are colliding with each other with the mean free path length L, but it moves with sound speed. So, the diffusion at micro scale is sound speed times mean free path length, but in hydrodynamics it is not. In hydrodynamics, these packets, these big packets of molecules are colliding with each other or transferring momentum and flux and stuff like that. And so, instead of mean free path length, I put the length of these eddies or length of this vortex and velocity of the vortex, multiply the two, and that will give me, I just multiply by L here, is L 4/3. So, my diffusion scale, diffusion coefficient is function of L, is L to the 4/3. So, my diffusion coefficient for heat diffusion was constant, right, but now it is L 4/3. So, this is a multi-scale phenomena and is a non-equilibrium phenomena, and from this I can derive another very important result. So, let us do it. What about the time scale? Is L by UL. So, just substitute UL from here, I get this, right. L divided by L 1/3 is L 2/3. Now, invert it. L squared is T cube by epsilon u. Okay, I just cube it and you get that. So, this is the diffusion length, or rather as I said, no, the heat diffusion 1 meter, how long will it take, the example we did. So, the L squared is goes as T cube. In what happens in random walker? L squared goes as T, right, that is a diffusion, right. By random walker, the distance travelled in time t will be square root of t, because it is going forward backward, but here it is not t, L squared is T cube. I think I did mention in the class that it is faster than ballistic. If some particle moves with constant speed, what is the distance travelled? L is proportional to t, right. So, L squared will be t squared, but I am doing faster than t squared. How is it possible? It is possible because we hop from a I gave this example in the class, I remember this one. So, my eddies are at small scale, I am going around, but then I jump onto bigger eddy, and bigger eddy has higher speed. So, example I gave, I go from a bus to train to flight. So, I go to flight, then the distance or the distance traveled is more on the flight, and that is what happens here. L squared is T cube, and this is called Taylor diffusion. Okay. So, in turbulence we have diffusion, which is T cube, L squared is T cube, and this is fully non-equilibrium. This is not an equilibrium phenomenon. Okay. And so, this is called Taylor diffusion. L squared is T cube, is a super diffusion, is faster than ballistic. Atmospheric flows exhibits Taylor diffusion. So, we are all living in non-equilibrium world now. I mean, this like thermodynamics does not work for atmosphere, and so this is a picture. Thermodynamic is equilibrium, but I am going to give an example here. So, this is what you should see. This is the hydro part, fluid part. So, I supply energy at large scale, and this is going into a smaller scale, like that. But then finally, at the smallest scale, it goes into thermal energy of the particles. These particles come into play. Of course, particles get heated by this process. So, this is called quasi equilibrium. Equilibrium should have constant temperature, but it is getting heated up slowly. This is quasi equilibrium, but this part is non equilibrium. This cascade, in fact, very strong cascade is going through this. So, this is non equilibrium plus quasi equilibrium. So, this is what is happening in this system. Okay, and the corresponding picture is there is a flux in this part, and there is a dissipation in this part, dissipation, and then this is the hydro part where this flux is 0, but there is some heating because of the energy coming from the smallest vortex. Okay. So, I think let us summarize it now. Turbulent phenomena is a non-equilibrium phenomena, it is a multi-scale, unlike equilibrium which is typically a single scale. Energy transfers break the detailed balance. So, we will perform field theory of turbulence next, that is my next task.